Hello everybody, and welcome to example 1. We are looking at the top of page 55, and this is the beginning of section 6.5 on improper integrals. And this is a brand new topic, and I'd like to start off the discussion with an example that I think will illustrate what we mean by an improper integral. Okay, so let's read this together. So we have a customer call center. They do a study and discover that the fraction of their customers who wait between t equals a and t equals b minutes to have their call answered is given by an integral a to b of 0.2 e to the minus 0.2 t dt. Okay, so the integral that we're staring at here is a way of measuring how many customers have to wait a certain amount of time. Okay, so a and b are times, and if you do the integral from a to b, you just figure out what fraction of the customers have to wait between those two times. Okay, so that's kind of the groundwork here. And the first thing they'd like us to do is to fill in a chart down here. Okay, so notice that in the chart they've given us various groups of waiting times, between 5 and 10 minutes, between 5 and 15 minutes, etc. We'd like to know what fraction of customers have to wait those times. Okay, so technically, we would need to do 4 separate integrals to fill in this chart, but one thing we might notice is that the lower limit is the same. Okay, we've got this 5 in every single waiting time period that we want to calculate, and so we can save ourselves a little bit of time by just doing the integral one time and integrating from 5 to b, where we can think of b as a variable that we're going to fill in, okay, once we've done the integral. So let's see if we can do this integral, and then we'll use it to answer the question above. Okay, well, what kind of an integral is this? You might notice that we can do this integral using a u substitution. Okay, if we let u be minus 0.2t, then du, let's see, derivative is going to be minus 0.2 times dt. Okay, go ahead and solve for the dt. And if we fill in the pieces here, let's see where this leads us. So we've got a 0.2 and e to the u, and then the dt is du over minus 0.2. We get a little bit of nice cancellation here, so the minus 0.2's go away. And let's see. So we are integrating, let's pull the minus sign out, and then antiderivative for e to the u is just e to the u. Okay, and then finally, we can fill the u back in from b to 5. By now, you might actually be able to do this integral without a substitution, doing this in your head. That's great if you can do that. I'm kind of doing it the long way here. And now we'll plug in the b and the 5. Okay, minus a negative is going to give us a plus e to the minus 0.2 times 5. Okay, I'm going to do one simplification here. So if you take 0.2 times 5, you actually get 1. I'm going to put those together and write this as minus e to the minus 0.2b minus e to the negative 1. Okay, there's the result of our integral. And again, we've left b kind of arbitrary. We don't know what that is. But here's what we can do now. Okay, if we go up to this part of our chart, for example, finding the waiting time between 5 and 10 minutes is like integrating from 5 to 10. All we have to do is to let the value of b, okay, down here in our integral equal 10, and we've got ourselves an integral. Okay, so I'm going to fill that in just over to the right here, minus e to the minus 0.2 times 10 minus e to, or I'm sorry, plus, oh, I just noticed a mistake here. This minus should be a plus. Sorry about that. Okay, that should be a plus e to the minus 1. Okay, and that's a number that you can calculate on your calculator, minus e to the minus 0.2 times 10 plus e to the minus 1. If you punch that in, what you get is 0.233. So what we figured out then is that 0.233 of our customers have to wait that long. If you like percentages, you could say 23.3% of our customers wait between 5 and 10 minutes. Okay, then what about the next one? If we want to do the integral between 5 and 15, now the value of b that we have down here is 15. So do almost the same calculation. Okay, punch that into your calculator, and this time what you'll end up with is 0.318. So about 31.8% of our callers have to wait between 5 and 15 minutes. Okay, and the rest is similar. All we're changing really is the value of b here. Okay, space is a little bit cramped here. And if you do those two calculations, here's what you should end up with. You can double check me. 0.350 and 0.361. Okay, so we can use this integral that we calculated down here to find the waiting time between 5 and any number of minutes. Okay, now here's where it gets interesting when we start looking at part B here. Okay, they ask us what fraction of our customers have to wait at least 5 minutes to have their call answered. Okay, how would we do that? Notice that there's no upper limit to the amount of waiting time. Now it's like asking you what fraction of the customers wait between 5 and forever to have their call answered. And so what would the upper limit of integration be in this case? Well, if there's no upper limit, it's like taking the integral from 5 all the way to infinity. Kind of strange having infinity as our limit of integration, and for that reason we give this type of an integral a special name. It's called an improper integral because of that infinity that's up there. Okay, and then the next question is, how do we actually calculate that? Okay, infinity is not a number, and so what we can do is to kind of break this calculation into two parts. So we'll first integrate from 5 to b, like we did in part A, and then after we do that integral, we'll let b approach infinity so that we get the range of time values that we really want. Okay, so to do this, we'll start by just doing the integral that's on the inside here, and we actually already calculated that integral and got this answer up here that I'm underlining from part A. So we'll use that calculation that we already did. Okay, and now the second part to finish this is we have to take the limit as b goes to infinity. Okay, and just to help us think about this, I'm going to rewrite the first term that we have here, this minus e to the minus 0.2b. Notice that there's a negative sign in that exponent, and so sometimes it helps to figure out what's going on, but to rewrite that. Okay, I'm going to move that into the denominator, which is going to change the sign on the exponent. Okay, and then e to the negative 1, I'm just going to leave that one alone. E to the negative 1 is just a number. Okay, and so here's what it comes down to, folks. We need to figure out what happens to this fraction as b goes to infinity. Okay, so my question to you is, if we took bigger and bigger numbers and substituted those in for b here, what would happen to this fraction that we just circled? Would it get bigger? Would it get smaller? The thing to notice is that the denominator of this fraction is going to go off to infinity, just the denominator part. Okay, and it's getting a little bit cluttered with my marking here, so I'm going to rewrite this. So we had negative 1 over e to the 0.2b, and we just made the observation that just the denominator part of that goes to infinity. So if you take a fraction and the numerator stays constant, -1, and the denominator gets bigger and bigger and bigger, the entire fraction actually goes to 0. So what we get after we take the limit is just the number e to the -1. That's something that you can substitute into your calculator, and what you get is 0.368 about. Okay, so what we have just figured out is that 36.8% of the customers have to wait at least 5 minutes, between 5 minutes and forever, to have their calls answered. Okay, and so just to tie this discussion together, let's fill this definition in at the bottom of the page. Okay, so we define the improper integral from a to infinity as follows. Okay, and it's going to be the same two-step process that we described above. Because infinity is not a number, we're going to first integrate from a to b, and then we're going to take the limit as b goes to infinity. 2 steps. Okay, and it turns out when you do an integral like this, there are actually 2 different things that can happen when you take this limit. First of all, it might exist and be finite, and in that case, we're going to use the word convergence. Converges. Okay, just a way of saying that we actually get a number, like this 0.368 that we have here. But another thing that might happen is you might take this limit and it might go off to infinity, for example. Okay, instead of getting a finite number, and in that case, we will call it divergence. Okay, and in future examples, we'll see examples of both of those behaviors.